So 2023 January paper 2, 2023 January paper 2. Right? Question 1 reads as follows: define the period of a simple pendulum. Right? So basically, if you have a fixed support over here and you pull the pendulum, let's say to this side here, and we say this is position A, right? And you pull it to this side, right? Position A, and then you release it and allow it to swing. It goes swing to position B, like that's over here, and then it go come back to position A, right? So it go to position B and come back to position A. So we can use that there, this little diagram here. This is the fixed support up here. This little diagram here to define the period of a simple pendulum. So the period of a simple pendulum is the time period symbol is capital T for the pendulum pendulum, right, is the time it takes for the pendulum, the pendulum bob, or the pendulum, if you want to say, from the pendulum bob to swing from side to side and back to its original position. Right, so it's basically, if you want to say, you could say is the time it takes for the bob to swing from A to B and then back to A, if you want to say it like that. Right, the unit for period, which is T, the unit for T, which is period, is really seconds. Period is measured in seconds, right? Because it's a measure of time. Now part B, the table 1 shows the results of an experiment to find the relationship between the length of a string L and the period of the pendulum T. Let's say table 1, length of the string L and corresponding period values of a simple pendulum T. So the length of the string, as you can see, it is increasing as you're coming down the column. The period values are basically increasing as well. So as you increase the length, the period value increasing based on this data here. They want you to fill out period square, this column here. So I'll do a sample calculation here, and you can use this for the others. So sample calculation. Right, so the first one would be period squared, right? So it's period is 0.77. You need to square this. That because 0.77 is really t. Look at here. If you square that, you'll get t squared, which is really, use this in the calculator, plug in this in the calculator, you get 0.59. You can put that here 0.59. Now all your values in this table coming down here needs to be to the same decimal place, right? So this will be 0.98. This will be 1.32. This should be 1.80. This should be 2.19. This should be 2.62 and 3.06. Right? Just plug in the respective period values in the calculator, square it, and you should get the respective t squared values. Understand this, right? So now we're going on to part two. Well, part one here, right? Part one. Steady independent variable in this experiment. Now, in case you didn't know what independent means, it basically means manipulated variable, right? If you don't know what manipulated means, that means change. So steady variable that you're really changing, right? Here, the only thing you can really change here is the length of the string, right? The length of the string. So let me see. You have the fixed support here. This is the length of the string basically here, right? And here your bob attached. So you could lengthen it, get it longer. Basically, that's what it was doing in the experiment, right? So we can say that that is the length of the string, right? So the length of the string, right? Steady independent manipulated variable in this experiment, right? We did that. This is a complete table one by certain period squared values in column 3. We already do that. So that's our easy 5 marks right there. Now let's say using the grid provided in figure 1, my bad. On page 5, plot a graph of period squared versus length. A lot of students just make mistake with this, right? And they just plot the wrong thing on the y-axis, right? Whatever quantity is stated first, just go on your y-axis. Because they say period squared first, they put that word first, that will be going on your y-axis. Whatever is stated second, just go on your x-axis. You need to know this, right? A lot of students still mix up this. So your graph will look something like this. This could be length, right? And this could be t squared or period squared. I'm not going to put the whole word there. That is t squared. Because your vertical axis is your y-axis, your horizontal axis is your x-axis. And when you plot your graph, typical experiment, I guess you get a straight line to your origin. So if you don't get something like this, you do something wrong there. Right? For period squared versus length, you should get a straight line. This is the graph that I got when I plotted. Hopefully everything is correct. I can barely see there, but let's see. So here we start both axes at 0, 0. If you start x on your y-axis at 0, 0, you need to state that. I stated that, right? Next thing is get marks for is the scale. Notice I increased by 0.4 from 0 to 0.4. The difference is 0.4. Here the difference is the same 0.4. 0.4 plus zero point 0.4 is 0.8. Difference here is the same 0.4. Here is the same 0.4. Here is the same 0.4. Notice the spaces between them are the same as well. Every 2 centimeters is 0.4. Right? Here is the same thing, 0.4. This needs to be consistent for you to get your full marks. If it is off, you will lose marks, right? So that needs to be consistent. Same thing for your x-axis. It needs to be consistent, right? So let's look at it. So here should be, well, the difference is 0.1. You increase by 0.1. Keep increasing by 0.1, basically. Right? Me how to go through all of that. So if you need to keep increasing by 0.1. Right? So let me just clean up this part here now. Um, that's basically what we call that scale, right? You get your marks for your scale there. You have to label your y and your x-axis. So notice I put period, comma t squared, and I put the units second squared. You get marks for that. Length, comma, the letter representing the symbol for length, which is L, unit in bracket meters. You get marks for that. Right? Title, I put that as well. Y-axis, I put that. X-axis, I put that. Right. Now it's just to plot your points. Now I had went through these points already, assuming that they're correct, right? So I went through this already. Didn't really double check it, but assuming it correct, right? So plotting your points, but we're gonna know if we correct after. But plotting your points, you'll get marks for that as well. Plotting your points correctly, right? You draw a best fit line. Notice the line just passing through like 1 or 2 points from my data, or just like 1 point. Because this one kind of off here, right? But it don't need to pass through all the data points, right? And next mistake students is make, they just try to make the line fit through all their points, right? And they go do this, connect it like that, connect it like that. No, that's wrong. You have to draw a best fit line through your data points, right? You'll get marks for that. So notice I have a few points just above the line, and I had this point here below the line to compensate for the 1 or 2 points that are just above the line, right? Um, so that's basically the graphing part there, the graphing analysis part there, right? And that is give away 8 marks. Simple, right? So let's say to calculate the gradient of the graph, and this is 6 marks. So you're not just going to get your marks for your gradient, I assume, and you'll get marks for your unit and stuff like that as well. You gotta put your formula for the gradient and thing too. So I'm gonna put S for gradient because they say gradient, comma S, which means like gradient. That is equal to y2 minus y1 all over x2 minus x1. Now, this is a fixed formula. Any straight line has this formula, right? All straight line has this formula for the gradient. So this is a fixed formula for the gradient of a straight line. But you gotta get these x2, x1, y2, y1, all them thing. You gotta get that. So you just get that straight from the graph. Now you had a read of 2 points that is exactly on the straight line. So I kind of ratchet this one a little bit here, and I say this is 1.5 comma 0.6. Notice something from the table. I had 0.15 and 0.59. Here I have, so that's a little error that I have here. So this supposed to be 0.15 actually, right? So I'm gonna try to fix that there one time. So this is 0.15, right? Because if you read comment down here, this is 0.15, right? Right, so that is 0.15 there. So I'm gonna write down that point there one time. Right, so I'm put down that here. The first point would be, I could put that up here, 0.15, comma, the y1 was 0.6, where we come across here is like 0.6. So 0.6. And the other point would be coming up here. This is the point that I read up here. This is 0.8, 3.16. 3.16. Just below. Well, one square below 3.2, which will be 3.16. Right? So let's go 0.8, 0.8, 3.16. Notice something. This to calculate the gradient on a different page, right? So you want to make sure that your the value that you're pulling off from your graph is exactly what you're writing on this new page here, right? You don't want to make an error in writing a wrong point here. You're going to throw off your gradient value, right? Before I go on to that, some students is given issues reading what is one of the small square in between. If this is 0.4 here, and you have 10 small squares in between here, this is 10 small squares here, 10 small square is equal to 0.4. So one of the small tiny squares actually 0.4 divided by 10, which is really 0.04, right? So if I know one of these small tiny squares 0.04, and I know up here is 3.2, then 3.2 minus 0.04, that will give me 3.16. And this makes sense because this is just below one of the small squares from this solid dark line there. So that will make sense for the 3.16. Right? That is just how to read off the small tiny increments in between. Right? So now we can just plug in these values here. So you want to put the first point as x1, y1, and the second point as x2, y2. This is how I like to do it. And then you make a substitution here now. So instead of y2, you're going to replace that with the number 3.16, right? Minus y1, which is 0.6. Now we're doing our substitution, so I'm writing this in brackets. All over x2, which is 0.8, 0.8, minus x1, which is 0.15, right? So you just have to work out that there now, right? So we can work with that. 3.94. If you round it off and put it into decimal place, right? It will be 3.94. Now, this is 6 marks, so I assume there were the units too. So we put back S for the gradient. That is really given by the change in y all over the change in x. Right? But what is on our y-axis? If we look back at our graph, period squared or t squared. The unit is s to the minus, s to the power positive 2 second squared. So I put in the unit here, s squared, all over what is plotted on your x-axis length, and the unit is meters, m. Right? Right? So notice this. If you bring the m on top, it could be m to the minus 1. So you have s to the power of 2, m to the minus 1. That is your unit. So if you want, you could put the final answer for s over here. I go put it here. I go say s is equal to 3.94 s to the power of 2 m to the power of minus 1. And that is my answer there. And this will, I believe this will guarantee 6 marks, right? Answer with unit, right? Very important. Now the next part, let's say given that s is equal to 4 pi squared all over g, calculate the acceleration due to gravity, right? So let's see. Remember, s is your gradient, eh? And let's say acceleration due to gravity. Well, we know gravity for CXC could be 10 meters per second squared. That is the acceleration due to gravity. Or you could say it's 10 Newton per kilogram. Right? So we know we had to get a value around this, but when you go on to keep on it, it'll be like G is equal to 9.81. It could be like that, right? Meters per second squared. Well, we trying to get a value like that, so let me see what we gonna get here. So we know that they tell us S is equal to 4 pi squared all over G. You could write that a lot better, right? Anyway, 4 pi squared all over G. So you want to solve for G. So I can write S as a fraction, S over 1. right? If I had the number 10, I could write 10 as a fraction, 10 all over 1. If I have the number 2, I could write 2 as a fraction, 2 over 1. So if I have s, I could write s as a fraction, s all over 1. Because anything divided by 1 is anything, right? So I write s over 1 just to have it in the fractional form, right? So now that I can cross multiply. So I wanted it in fractional form so I could cross multiply. So I say s by g and then 1 by 4 pi squared. So what I'm going to end up with here now is s multiplied by g is equal to 1 by 4 pi squared will just be 4 pi squared because they just multiplying it by 1, right? And you're solving for g. G can be equal to 4 pi squared all over s, which is your gradient. So now you just substitute that. So you write 4 pi squared all over s. But what is s? We get s to be 3.94. 3.94. Right? Remember, we could just put in units there one time. It was s to the power of 2 m to the power of minus 1. So g is equal, when you type in this in the calculator, 4, I can just put pi squared divided by 3.94. I gain 10. 10, yeah, 10.02, right? Meters per second squared. Now you might want to know how I get 10 meters per second squared, right? So let me just show you that one time. If I have 1 all over x to the power of n, I can write this as x to the power of negative n. And if I have 1 all over x to the power of negative n, I can write this as x to the power of positive n. Law of indices, right? So I have s to the power of 2 as the denominator, but I want to bring this on top. So if I bring it on top, it will be s to the power of negative 2. And I have m to the minus 1 at the bottom in the denominator. So if I bring it on top, I'll have m to the power of positive 1. Applying this one here. So I have m to the power of positive 1 or just m. Notice something. I had given you g is equal to 10 meters per second squared here. That was the unit. For acceleration, we proved that the units are correct as well. Right? We know gravity was 10. Well, if you want to write this to 1 decimal, if you want to write it as a whole number, you could say g is therefore equal to 10 and then put meters per second squared. And that's the answer there. Right? Understand this? Nice, right? So you see how we proved that there, the value of gravity, right?